In this video, we're going to talk about three vectors that kind of move along with a curve as you trace out the path that have a key significance in terms of things like velocity and acceleration. What's interesting is that even though acceleration and velocity are things that are unique to our parameterization, these vectors are actually intrinsic to the curve itself. And you'll get the same answer with an asterisk next to that, no matter how you parameterize. So let's go ahead and talk about these vectors. So first we're going to have the unit tangent vector, and this is a vector. I should also say these vectors are all going to be orthogonal to each other. So the unit tangent vector is a vector that is going to point in the direction of the velocity. The principal normal vector is going to point in the direction of t prime. So it's going to point in the direction of the derivative of the unit tangent vector. And that magically will end up being perpendicular to the unit tangent vector. And then we have two perpendicular vectors. How do we get one that's perpendicular to both of them? We're just going to take the cross product. So this vector will be exactly t cross n. And this is called the binormal vector. So we kind of already have our formula for the binormal vector, and we can figure out the formulas for the other. If we want something that is points in the direction of the velocity, but we want it to be a unit vector, we want it to have length 1, what we'll do is we'll take the velocity vector and divide it by the norm of the velocity vector, or divide it by speed. We'll do a similar thing with the principal normal vector. We'll go ahead and take the derivative of the unit tangent vector and divide it by the norm of the unit tangent vector's derivative. Then, as I said earlier, we already pretty much have our formula for the binormal vector. So let's go ahead and practice finding these three vectors for our curve. Now, what makes this problem really nice is that we previously found that the speed, or the norm of the derivative, is a constant function. It's just 5. Often, that won't be the case. You'll actually have some t's floating around here, which is going to make finding these other things fun, except not. But in this case, since the speed is constant, it's going to help out. So let's take a look. To find the unit tangent vector, we start by taking the derivative of our path. We already did that previously, but we'll do it again. That's going to be negative 3 sine of t, 3 cosine of t, 4. And now we're going to divide by the norm. So we're going to divide by 5. And we can go ahead and rewrite that as negative 3/5 sine of t, 3/5 cosine of t, 4/5. Okay, so that's done. We found our unit tangent vector. And it helped that we'd already found the speed. Now let's go ahead and try to find the principal normal vector. We need to start by taking the derivative of our unit tangent vector and then divide by the norm of that. So what's the derivative of this thing? Well, that's going to be negative 3/5 cosine of t, negative 3/5 sine of t, and then just 4/5, the derivative of 4/5, that's a constant, so it's just going to be 0. And then we need to find the norm of this thing that we just had. So that's going to be the square root of, I'll go ahead and square each of these terms in my head. So that's going to be 9/25 cosine squared of t plus 9/25 sine squared of t. And then 0 is just 0. So this will actually end up being just the square root of 9/25, which ends up just being 3/5. Okay, that's really nice. And that maybe isn't the most surprising thing you've seen in your life, because we know that negative cosine, negative sine is a vector with length 1. So it shouldn't be surprising that basically when we take the norm and divide out by the norm, we're getting rid of that constant 3/5 out front. So all that to say, our principal normal vector will just be negative cosine of t, negative sine of t, 0. Okay. And we have one more to find, and this will probably be the most annoying of them all. We need to find the binormal vector, which we find by taking the cross product of our two previous vectors. So I'm going to have the cross product of negative 3/5 sine of t, 3/5 cosine of t, and 4/5. That cross product with negative cosine of t, negative sine of t, 0. Remember, we're going to rewrite the first two columns. And then let's go ahead and take that cross product. So we'll have a 0 term for that I. We'll have minus 9/5 cosine of t, j. Then we'll have plus 3/5 sine of t. That's a 4, not a 9. Silly me. Plus 3/5 sine of t, squared of t, actually, because we have sine of t and sine of t there. Then if we go the other way, we're going to have minus 4/5 sine of t, or plus 4/5 sine of ti, plus 3/5 cosine squared t, k. And then j, that last term, is going to be 0 because we have the 0 there. So if we put this all together, we're going to end up with 4/5 sine of t for our I term. For our j term, we're going to have negative 4/5 cosine of t. And then for our k term, we're going to have 3/5 cosine squared of t plus 3/5 sine squared of t. That's just going to be 3/5. And that will end up being our binormal vector. And one way that we can check that we're hopefully right is if you notice this does have a norm of 1. And we want this to be a unit vector. It turns out that since the first two are unit vectors, when we take the cross product, we'll get another unit vector, so that's nice. And there's probably some other things we could check, like for example, we could dot it with one of our vectors to see, hey, am I going to get something that is 0 if I dot it with one of the vectors that gave me the cross product? The answer is yeah. We'll get negative 4/5 sine of t cosine of t if we dot with n. As our first, and then positive 4/5 sine of t cosine of t, and then 0. Add those all up, that's going to get you 0. So we notice that this is in fact orthogonal with n. That's a good safety check that we did this problem right. And yeah, so we found all three of our vectors here. Collectively, we call these the moving frame vectors because, again, they move along with the curve and they kind of give us a frame that helps us think about velocity and acceleration. So there you go.